Bismillahirrahmanirrahim. Wassalatu wassalamu ala rasulillah. So today we will solve recitation problem for chapter 30. Let's start by the first problem. By the way, we have solved this recitation problem. So I'm just recording it for your own information. But we have solved this problem, this problem, this problem, and this problem. You know, which are the main representative of all the rest. But let me go through them step by step. So I remind you that these problems, how easy they look. I think less than 60% of students got it right. But it's easy. Let's look at it. So we have here a 25-turn circular coil with a radius of 50 centimeters, and it's placed in a uniform magnetic field of magnitude 5 Tesla. If the magnetic field makes an angle of 25.8 degrees with the plane of the coil, what is the magnitude of the magnetic flux through the coil? Okay, so this is just N. Number of turns is 25. The radius is given 0.5 meters. You put everything in SI units. Okay? And I give you the magnetic field magnitude B is 5 Tesla, and it's uniform. And the magnetic field is making this angle with the plane of the coil. Okay, let's assume that the uniform magnetic field is in this direction. So my uniform magnetic field is in this direction, and these are the magnetic field lines. Now I have a coil here, which is making a certain angle. So this coil has N, which is 25 turns, you see? So it's a coil. And this coil, the plane of the coil is making an angle, so B, let's say this is B, an angle of 25 degree, 0.8 degree, with the plane of the magnetic field, okay? Great. So I'm asking you to calculate the magnetic flux. The total magnetic flux, of course, capital Phi B is number of turns multiplied by magnetic flux going for each turn, for each circle. Okay? So it's N phi B. Okay? So it's equal to N integral of B dot dA. But B is constant, so I can get it out of the integral. So N B dot A. Okay. So this is N B A cosine the angle between B and A. Now I want the angle between B and A. Okay. Of course, B is here. Now what is A? A again is normal to the surface of the coil. So A is along the normal. Okay. And this is 90 degree. Let me take another color. Okay. So this is 90 degree. Okay. Remember, this is the plane of the coil, and the angle between A, which is this angle here, this vector here, and the magnetic field is this angle. So this angle is 90 minus 25.8 degree. So it will be N, which is 25, multiplied by V, which is 5 Tesla, multiplied by A, which is pi R square, which is 0.5 square. Now cosine, which angle? 90 minus 25 degree, 25.8 degree. And this will give you 42.7 Weber. Okay. So the answer is here. So here, the only thing that you need to know is, and you have to be careful about this, is the area vector is normal to the surface of the plane of the coil. Okay. So it's normal to the plane of the coil. And the angle that I'm giving you here, this angle here, is the angle between the magnetic field and the plane of the coil. But I don't need that. I need the complementary of that angle. I need the angle between B and A. Basically, I need this angle here. This angle here is what I need, which is just 90 minus 25.8 degree. Okay. Again, don't forget to multiply by N, the number of turns. If the number of turns was 1, of course, I will just put 1. Next question. So now here in this problem here, I have 80 turn coil. So N is equal to 8. and I give you the cross-sectional area, 0.1 meter square, is placed in a magnetic field of 1 millitesla. So B is 1 millitesla, which is 10 to the power minus 3 Tesla. The plane of the coil now is perpendicular to the field. So basically here, this is my coil, and I have n turns on my coil. But the plane of the coil, which is this plane, is perpendicular to the magnetic field. So the magnetic field here, B, is normal to the plane of the coil. Of course, the area vector will be along the same direction, because the area vector by definition is normal. Okay? Great. So this is why I'm saying here. On the previous example, I told you that they are not perpendicular to each other. Okay? Great. So now the question is, if the magnetic field is reduced uniformly to 0, so B goes, this is B initial, and it goes to B final, which is 0, in 0.05 seconds. So in delta T, which is 0.05 seconds, calculate what is the EMF induced in the coil. Well, you know that EMF induced, Faraday's law, is derivative minus derivative with respect to time of phi B. Don't forget the N, of course, okay? Because I'm looking for the total flux. N is the number of turns. So this is equal to minus N derivative with respect to time of what's the magnetic flux here? Again, magnetic flux is integral of B dA. Of course, here B is uniform. Basically, B is, when I say uniform, I'm talking about spatial uniformity. Of course, B is variable, it depends on time. But B is uniform in space. So basically, B being uniform, I can put the B out of the integral. So I have just BA, which is magnitude of B, magnitude of A, cosine the angle between them. Okay, great. So here I'll have derivative with respect to time of BA, magnitude of B, multiplied by magnitude of A, multiplied by the cosine between the angle of B and A. Of course, it's 0. Okay, they are parallel to each other. So cosine 0 is just 1. So I will end up with minus N. Of course, A is constant, so I'll put it out, and then I'll have just dB over dt. Again, I want the EMF induced absolute value, so I take the absolute value of everything here. So I will have NA dB over dt is just absolute value of the slope. So it's B final minus B initial divided by T final minus T initial, which is delta T. I know everything. I know N 80. I know A 0.1. I know B final minus B initial absolute value. Of course, this will give me 10 to the power minus 3, 0 minus 10 to the power minus 3. But I take absolute value divided by 0.05. And you calculate this. Of course, it will give it to you in volt. So you get 0.16 volt. And we already solved this in class, by the way. Let's go to the next problem here. Read the problem very carefully. We have solved it in class, in recitation, but I will solve it again. So here we have two frictionless conducting rail separated by a length L of 55 centimeters. So L basically is 0.55 meters. Put it in meters, of course. They are connected through a resistor R, which is 2 ohm. You see, I'm giving 3 significant figures, 3 significant. I want my answer in 3 significant figures, of course. Okay, the circuit is completed by a bar that is free to slide on the rail. Okay, so you have this bar here. It's free to slide. Of course, this junction here between the bar and the rail is frictionless. A uniform magnetic field B out, directed out of the page, you see, this B here, it's out of the page. It's uniform, is present in the region. The question is, what is the magnitude of the force Fp? So I'm applying here this force Fp. So what should be the magnitude of force Sp such that the bar will move at a constant speed, and I give you V. So V is constant and is equal to 1.25 meters per second. So what should be FAP? Well, since V is constant, that means the acceleration should be 0, meaning FP, the force that I applied, should be counterbalanced by a magnetic force, okay, FB. And this should give you 0. The net force should be 0. In other words, I'm just telling you that okay, so FP is this direction, of course, FB, which is a magnetic force, should be in this direction, equal in opposite to FP, okay? Same in magnitude, but opposite in direction, okay? So FP is just FB. Okay, great. Now, what is FB? Of course, we already demonstrated this in class. So basically here, FP will have a tendency to increase the flux. So phi B will be increased, phi B will be increasing, the flux will be increasing because of FP. So that means I will have an induced magnetic field that is resisting what? That is resisting the increase of flux. So let me take another pen here. You remember that Faraday's law is d phi over dt. And Lenz law is giving me the sign of this minus sign here, okay? So Lenz law is telling me that the EMF induced will oppose the increase or the decrease of flux. Basically, the EMF induced will oppose the change in flux. So here the flux is increasing because I am increasing the area. So I will have an induced magnetic field. What do you think? It should be in which direction? Because the induced magnetic field will be pointing inward. This is B induced. So this will be the direction of the induced magnetic field. Of course, if the induced magnetic field is inward, of course, my current induced will be in this direction. So the current induced will be in the clockwise direction, okay? And you see, if the current is going in this direction here, of course, now if I use my right hand rule, you know that FB is I induced L cross B. I'm talking about the L, this L here. Okay? So if you use the right hand rule, you see that the magnetic force is pointing in this left direction, and it should be equal to FB. So what's the magnitude of FB? Of course, it will be I induced LB sine 90 degrees, which is the angle between L and B. This is just 1. So FB is just I induced LB. Now, what is I induced? We already calculated this. This is, of course, EMF induced divided by the resistance of the circuit. But what is the EMF induced? You can use Lenz law and you can use the formula sheet. EMF induced is just Faraday's law, LV. We already demonstrated this in class, divided by R. So I take this and I just plug it here. So I will have B LV divided by R multiplied by LB. Again, this L is small l. Okay, this L is this length here. Okay, we call it small l. So let me just call it small l here. Okay, because here I call it small l. You get my point. Now I will multiply by LB. Of course, I get that FP, which is FB, is B square L square V divided by R. Okay, so I know everything. Is 5 square, L is 0.55 square, V is 1.25, and I divide by the resistance, which is 2. How much do you get? Of course, you get 4.73 Newton. Okay, the first answer. And we solved this in class already. Yeah, but I'm just putting it for the sake of completeness. Okay, so we demonstrated this in class as well. Again, you can use directly that EMF induced is just DLV. Okay. Of course, you know what is B, what is L, what is V. Okay. Great. And of course, your I induced is just EMF induced divided by the resistance. And we already talked about this in lecture and in recitation also. Now, let me remind you something here. Of course, I demonstrated in class that, of course, Fp multiplied by the velocity v. This is what? This is, of course, the rate at which the applied force is doing work. Okay. This is the power. Basically, this is the power. This is the power of the applied force. Okay. Fp multiplied by v. You remember F dot P, this is the power. This is the rate at which the applied force is doing work. And we can demonstrate that here. You see, we already calculated Fp. It's just B square L square V divided by R. Now I multiply by another V, I have this. So Fp multiplied by V, this is also B square L square V square divided by R. Okay. And we talked about this in class and we derived it. And I told you that write down this formula, if you remember correctly. Okay, great. Now this power is equal to the rate at which the thermal energy is dissipated in the resistance here. Okay. Now, because of this current induced, which is passing through my circuit, through this resistor, I have thermal energy dissipated. So thermal energy dissipated, the power of a resistor when it's carrying a current I is just I square. Of course, it will be I induced I square R. Okay, or this is just equal to EMF induced square divided by R. Sorry. Yes, it's this. Yes, sorry. So it's EMF induced square divided by R. Okay. And this by definition is rate at which thermal energy is dissipated in the resistor, dissipated in R. Okay, and this again is equal to just B square L square V square divided by R. Okay, I will ask you this later. Okay, so of course, since I am pulling the bar out, there is a magnetic force opposite to my force, so there is a resistance. Okay? It will resist the motion. Lenz law, Faraday's law. And of course, the work or the power I am doing will be equal to the power dissipated by the resistor. Okay, let's solve the next question, which is also the same thing. So here I give you now, same thing now. Now, the magnetic field is pointing inward, right? So we have a metal bar. I give you the length of the metal bar. This is L. And this is this length here. So I give you the speed, V. So I give you the resistance, R, 45. And I tell you that the magnetic field is here. And B, 0.65 Tesla. Now I'm asking you, what is the rate at which the applied work is doing force? Same problem. Okay? Now I'm pushing the bar in. Okay, so the V is this way. And of course, the magnetic field is pointing out. What do you think? What should be the direction of the induced current? Of course, the induced current will be going clockwise, counterclockwise. It will be going in this direction. So what do you think? The magnetic field. Of course, the induced magnetic field is pointing outward. Okay, and this should be very clear. Induced current is going in this direction. Anyway, what I want to find here is the rate at which the applied force is doing work. Well, we already demonstrated this. Applied force multiplied by V, this gives me the rate at which the applied force is doing work. And this is just equal to B square, L square, V square divided by R. So you put all your numbers. B square, what is B square? 0.65 square, L square, 0.32 square, V square, 5.5 square, divided by the resistance, which is 45. And of course, you will get this number, which is 29 milliwatt. Okay, this is the right answer. Okay. And of course, we already demonstrated that this should be equal to I induced square multiplied by R. In other words, this is just, of course, EMF induced square divided by R. Okay? Because you know that I induced, of course, is EMF induced divided by R. You just take this and you plug it here. And this is what you will get. Okay? Now, EMF induced is what? BLV. Now, square, B square, L square, V square divided by R. Surprise, surprise, of course, I get the same answer. All the ways lead to Makkah. Yeah? If you take the right way. Yeah? Okay, so that's it. Next question. We have a conducting loop, and I give you the area of the conducting loop. It's this 5 centimeters square. Of course, we put it in meters square. So 5 centimeters square is 10 to the power minus 4 meters square. I give you the magnetic field. It's uniform, 0.35 Tesla, and I give you omega, 45 radian per second. So we have a conducting loop. Of course, here n is equal to what? 1. Okay. Otherwise, I will tell you n is equal to this, or a 25 turn loop. So you know that n is equal to 25. Here, n is equal to 1. Of area A, okay, is parallel to YZ and as shown in the figure 15. It is placed in a uniform magnetic field and it's rotating about the y-axis. So of course it's rotating around this axis here, which is the y-axis. So it's rotating this way, okay, with an angular speed. Of course, the angular speed is constant. So the question is, what is the maximum induced EMF in the loop? So here I gave you the angular speed. I'm giving you theta. So theta is just omega t, which is 45 times the time. Okay. So as you know, the induced is just minus d phi over dt. But here I want the magnitude, so forget about the minus. Okay. You just take absolute value. Okay. So d over dt, now what's the flux? Of course, the flux is NBA cosine theta. So n is equal to 1, and it's a constant. I can put it out. B in magnitude is constant, of course, and in direction also. Now A in magnitude is constant. What is varying here is the theta. Okay. So you remember here we have flux is just n B A cosine the angle between B and A. Okay, so here this is constant, this is constant, this is constant. What is varying is this angle theta here. Okay, it's like an electric generator. Okay, great. So I put the constant out of the derivative. Now, what's the derivative of cosine theta? Derivative with respect to time of cosine theta. By the way, theta is omega t. Okay, that's why I gave you omega. So this is minus omega, of course, sine omega t. So the omega comes out, and of course I have sine omega t. Now I take absolute value, of course the minus goes away. Okay, so you see that, of course, as we said, the EMF induced here is an AC. Okay, basically it's alternating. Okay, it's following a sinusoidal form. So this is the amplitude, and this is between -1 and +1. So of course the amplitude is just this NBA omega. N is equal to 1, so I have BA omega, and I know everything. I know B, I know A, and I know omega I put everything in SI units. It will give it to me in volt, and then I will have this. This is the answer. Okay, like an electric generator. Okay, so this will produce, of course, AC current, and we already discussed this in class and in the recitation. Okay, let's solve the next problem. Same as before. So here I give you L, which is 1.5 meter. So it's pulled to the right. And I give you the steady speed. V is equal to 5 meters per second, as you can see here. V is equal to this, and I give you the uniform magnetic field, B here, and B is pointing inward. Okay, as you can see, it's pointing inward. And B is 0.75 Tesla. So the bar rides on a parallel metal rail, and if I give you R as well, 25 ohm. What is the current induced in the circuit? Oh, come on, guys, now you know. Okay? Current induced in the circuit will be EMF induced divided by R. So this is VLV divided by R. I know B. What is B? 0.75. I know L, 1.5, and I know V, 5, and I divide by R, which is 25. How much do you get? Of course, you will get 0.225 amp. So that's your magnitude of current. So it's either this one or this one. Now, what the direction? Is it clockwise or counterclockwise? Look here. Of course, my F applied is going in this direction. So F applied is going to the right. So F of magnetic field will be to the left, FB. Okay, and this shows you that, of course, what's the direction of your current? What do you think? If F apply is to the right, so your current is clockwise, counterclockwise, is going in this direction. So E induced is going in this direction. Current induced is going in this direction. Okay. The other way to look at it is basically here, my F applied is increasing the flux. So FP is increasing the flux because it's increasing the area. You see, the area is increasing, so they're increasing the flux. Don't forget that the magnetic field is in. Now, Lenz law is telling you that my B induced will oppose the change in flux. So B induced should be outward. Do you agree with that? So B induced should be outward. Okay. Now, if B induced is outward, what should be the direction? Of course, my current is going counterclockwise. Of course, if B induced is outward, so I induced is going counterclockwise, okay, in the positive direction. So this is the correct answer, the first one. Okay. Two ways to see the direction here. Okay. You look at if I have an increase or decrease of my magnetic flux, and you know that Lenz law will oppose that change in magnetic flux. So here it's an increase, so my Lenz law, my B induced should oppose the increase of magnetic flux. So it should be outward. Now outward, well, I use my right-hand rule, and I see that my current is going in the counterclockwise direction. The other way to look at it is basically my FB should oppose this FP. So what should be the direction of current such that FB, which is I induced L cross B, is opposing? Of course, it's the counterclockwise direction, so it should go up here. Next. Okay, I think I solved this problem as well. Okay, it's straightforward, so I can skip it even. So I will not discuss, but I will ask you to read the question, and I will just write the formula. So here I give you the radius is 0.15 meters, and I give you the magnetic field, which is what? 0.15 Tesla. So here I'm just playing with the area. So you know that the magnetic flux is what? BA, cosine between B and A. So here the angle is 0 degree. So it's just BA. B is constant, as I said it. But the thing here, which is varying, is the area. Great. So EMF induced is just minus d phi over dt. Let me take the absolute value because I want magnitude. That's what I said. What's the magnitude here on average? So I have absolute value d over dt of dA. Of course, b is constant. I get it out and I'll have d over dA. I mean, derivative of A with respect to time. And that I gave it to you already. So this is B absolute value, A final minus A initial divided by delta T. So I gave you everything in this problem. Let's just do it. B is 0.15 Tesla. A final is 0. Area initial is pi r square, which is 0.15 square, divided by time, which is 0.2. And you take the absolute value and then you will get everything in volt. If you look at it in volt, you will get 0.053 volt, which is 53.0 millivolt. Next question. Okay, let me erase this. So we have solved this also in class. Okay, we have figure 16, which shows three situations in which a wire loop lies partially in a magnetic field with the battery as a part of the loop. Okay, so here I have battery. And here, of course, the EMF is going in this direction here, so minus to plus. You remember, this is the EMF of the battery. The EMF of the battery is going in this direction here. And this is the EMF of the battery, which is going in this direction. So EMF of the battery going in this direction, the current of the battery is going in this direction. In the first case, it's going counterclockwise. In the second case, it's going clockwise. This is the current of the battery. And in the third case, it's going also clockwise. Great. Okay. Now, the question now is, what is the induced EMF? The induced EMF, now the question is, the induced EMF and the battery EMF have the same direction in which case? Case 1 or case 2 or case 3. In case 1, we have a magnetic field pointing out towards you and increasing. So if it's pointing out and increasing, well, let me apply Lenz law. E induced is just d phi over dt, d phi magnetic flux, derivative with respect to time of the magnetic flux. So here I will be using the minus. This is Faraday's law, by the way. Okay, Faraday law of induction, as we discussed in class. This is the Faraday's law of induction. Okay. Now this minus sign is just Lenz law, so it's embedded in the Faraday's law, and it's telling you that the induced EMF, the induced magnetic field, is opposing the change of flux. So here I have B here, which is pointing outside towards you, and it's increasing. So my induced magnetic field will be inside. So if I have induced magnetic field inside, now I can use the right-hand rule. So what should be my induced current? Magnetic field inside, induced current will be in this direction. So induced current, this I induce, is opposing the current from the battery. So this is not correct, okay? Because I want the induced EMF and the battery to be in the same direction. So the induced EMF here is in this. So I have minus here and plus here. And these are opposing. So this induced EMF, E induced, is opposing the EMF of the battery. That's not what I want. Okay. Now in the second case, B is inward and it's decreasing. Now if it's decreasing, Lenz law is telling me that of course my B induced should be in which direction? What do you think? B is inward and decreasing. So I don't want that to decrease. So I will put a magnetic field inward because I don't want it to decrease. So B induced is inward. Now B induced being inward, what the direction of the current induced? The current induced will be also, as before, clockwise. Okay. And current induced now is in the same direction as the current of the battery, because the EMF induced is like this. So this is plus and this is minus, and this is EMF induced. Okay, and you see that the EMF induced has the same direction as the EMF of the battery. Okay, they current are going in the same direction. Okay, the current of the battery, which is going clockwise here, is going in the same direction as the current induced, which is going clockwise. So this is correct. Okay. So this is correct. By correct, I mean the EMF induced and the battery have the same direction. Okay. Now let's check the last one. Now B is out. Of course, B is in the lower part of my circle here. So B is out and it's decreasing. So B is out and it's decreasing. So what should be the direction of my B induced? Of course, B induced is also out. Now B induced out. What the direction of the current induced? Of course, the current induced will be going counterclockwise. That means my EMF induced is B in this direction. This is minus, this is plus, and this is EMF induced. And you see that the EMF induced is opposing the EMF of the battery. They current are opposing each other. One, the current of the battery is going clockwise, the current of the EMF is going counterclockwise. So of course, A is the right answer. Only 2 is fulfilling what I want. Okay, let's look at this problem also, which is also the same, but let me solve it again. Figure 15 shows 4 square loops moving in or out in a uniform magnetic field directed into the page. You see, it's a cross. This is into, of course, into the page, or inward, in the page. Of course, this is out of the page, outward. And all of them are moving at constant speed. Okay? And all of them are identical, meaning the L is the same. Okay, now, in which of the following situations the induced current in the loop is clockwise in direction? So I have here 1 and 2. Basically 1 and 4 are going out. 2 and 3 are getting inside the magnetic field. Okay, let's start by 1. 1 is getting out. Oh, okay, interesting. Now, am I increasing the flux or am I decreasing the flux? Of course, I'm decreasing the flux because I'm decreasing the area inside the magnetic field. So flux is decreasing. Now my B induced will oppose that decrease of flux. So my B induced will be in which direction? It will be in. Okay. Now B induced in, that means my current induced right-hand rule is going in the clockwise direction. Okay. So E induced is going in the clockwise direction. Okay. So 1 is correct. So it's either this or this. Now, of course, 4 also. Okay. 4, it's getting out. So I'm decreasing the flux. So my B induced does not want that to happen. So B induced will be in. Of course, this using right-hand rule, you see that the current induced is going in which direction? Of course, the current induced is going also clockwise. So A is the correct answer. Now let's check for 2 and 3. 2 is getting in. Now I'm getting in, I'm increasing the flux. So Lenz law is telling you I don't want that increase of flux to happen. So that means my B induced will be out. B induced out. Of course, current is going in which direction? Counterclockwise. Okay, the current induced is going counterclockwise, and also here the current induced is going counterclockwise. Okay, great. So of course 1 and 4 are the only correct answers. This and this. Okay, because the current is going clockwise here. 3 and 4, because the current is going counterclockwise. Okay, we have already solved this, but I can solve it again. You already have solved this, but I can solve it again. Straightforward, okay? And this also, you can solve it easily. Let me just discuss them very quickly. So here I give you the loop of area. Basically, area is 4 centimeter cube, which is 4 10 to the power minus 4 meters square, centimeter square. And I give you the resistance 5 micro ohm, which is 5 10 to the power minus 6 ohm. And it's perpendicular to the magnetic field. And I give you the magnitude of the magnetic field. B is 15 microtesla, 10 to the power minus 6 Tesla. And here, the magnitude of the the field drops uniformly to 0 in 3 milliseconds. So this is B initial, and B final is 0 in delta T, which is 3 10 to the power minus 3 milliseconds. The question is very simple. How much thermal energy is produced in the loop by the change in field? First, I have to get EMF induced. EMF induced is just N d phi divided by dt, basically d over dt of NBA. Because here I told you that, of course, the area, basically the loop, is perpendicular to the uniform magnetic field. This is the area of the loop, and the magnetic field is perpendicular here. And this is 90 degrees. Of course, the area vector is in the same direction. So my flux is just dA. Suppose I multiply by N if I have N loop. But here I just have one loop, one turn, so N is equal to 1. So this is just dA. Okay. Now, if I take the derivative with respect to time, the area is constant, but D is time dependent. Okay. So I'll have just A multiplied by the slope delta B divided by delta T. So I know delta B and I know delta T. I just plug in and I get my EMF induced. Now, once I get my EMF induced, I know the power dissipated by the resistance. The power will be just EMF induced square divided by the resistance, or current induced square multiplied by the resistance. It's the same thing, okay? Because you know that EMF induced is just resistance multiplied by current induced, okay? So it's the same thing. So here I just EMF induced divided by resistance, so I know the power, which is the rate of, let's say, dissipation. You know, power is just the rate at which the resistor is dissipating thermal energy, okay? So that means if I want thermal energy, I just have the power and I multiply by the time, okay? So I know the power, this is the power, and I multiply by the time and I get the energy. Power is energy divided by time. So if I want the thermal energy, I just take power multiplied by time, and that's what I did here, and I got it. Okay, is it clear? Great. So B and magnetic field, magnetic field and the area vector are parallel to each other, okay? Here, because I'm telling you that the loop is perpendicular to the magnetic field. Great. Well, this one is also the same thing, okay? So solve it and you realize that, of course, the current is here and it's going counterclockwise, okay? Here I told you that the magnetic field is increasing at this rate, okay? So if the magnetic field is increasing, the flux is increasing. Meaning what? Meaning that my Lenz law is telling me that no, I don't want that increase to happen. I don't want that change to happen. By the way, the magnetic field is pointing inward here. So if it's pointing inward and increasing, what should be my induced magnetic field? Induced magnetic field should be inward or outward? Of course, outward. So if my induced magnetic field is outward, of course, my current induced is going in this direction, which is the counterclockwise direction, okay? So the current induced is going counterclockwise, okay? And if I want to get the current induced, I just say that it's EMF induced divided by R. This gives me the current induced. Now, what is the EMF induced? Well, EMF induced in magnitude is just absolute value of d phi d divided by dt. Of course, with respect to dt. So here, you just have basically, d over dt of dA. A is constant, so you just have dB over dt. Okay, absolute value. So you have A. What's A? Is 8 square. 8 times square, of course, centimeter square, which is 10 to the power minus 4. And then you multiply by derivative of d with respect to time, and I gave you the rate of change, basically dB over dt. This is dB over dt, of course. This is 4.69 Tesla per second. And you calculate, this is what we calculate. And you get, of course, your EMF induced, you divide by the resistance, and you get the current induced. Of course, A is the correct answer. Okay, so this is also the same thing. Okay, I will solve it, so you will solve it. It's very straightforward. So here I'm asking you about the area. I give you the EMF induced, and I give you what is varying and how it's varying. So it's here. This is how deep the magnetic field is varying in time. Okay, I'm giving you this. I give you this, the right left-hand side, and I'm giving you the number of turns, and I'm giving you the angle between them. I said that the angle between them is 30 degrees, you see? And here, you see, this is what I said here. It's placed in a magnetic field so that the normal to the plane, meaning the vector A of the coil, makes an angle of 30 degrees with the fixed direction of the magnetic field. So I'm giving you directly the direction between B and A. And this is 30 degrees, and that's what I want, okay? So if I gave you the direction of the coil with the magnetic field, so you have to look at the complementary of that. Yeah. I hope you get what I'm talking about. Okay, great. And then your only unknown is A. You get it. Please, I gave you many other problems. You solve them, and inshallah, you'll do well in the exam. So I wish you nothing but the best. Okay, so I know that all these problems we already solved it in class, but I want you to have the recording just in case. Good luck for the exam. Assalamu alaikum.